Good morning, afternoon, or perhaps evening. My name is Tanya Amert, and I am about to present to you work done at the University of North Carolina at Chapel Hill. In this paper, we explored the price of enabling schedulability for a multi-object tracking application used in autonomous driving. In particular, we explored the trade-off between history and accuracy. An autonomous vehicle may require many applications to execute simultaneously. For example, path planning, and detection of slow-moving obstacles like turtles. Additionally, the vehicle may also be equipped to track fast-moving obstacles like rabbits in order to predict where they will travel next and take evasive action if necessary. These applications can be represented as processing graphs. From a certifiability point of view, the question arises as to whether we can guarantee bounded response times for all applications. Let's look at rabbit tracking in more detail. Given an RGB image taken from a camera, rabbit detection can be performed to locate any rabbits in the scene. Given information about where each rabbit has been in the past, their current positions can be predicted. These detections and predictions are matched, allowing the tracking information for each rabbit to be updated. The prediction step necessarily requires information that was an output from a previous time step. This introduces a cycle into the graph. Cycles can cause problems for response time analysis. If the most recent time step's output is always required, then each frame must be processed sequentially, and the cycle utilization must not be more than one. Recent work by our group provides response time analysis for cycles of arbitrary utilization by allowing frames to be processed in parallel. However, such parallelism means that the most recent results might not yet be available, potentially impacting the accuracy. This impact is what we sought to examine in this paper. Now that I've introduced the motivation for this paper, I will describe the history, response time, accuracy trade-off in more detail next. Then I will give an overview of the multi-object tracking application that we implemented and the Carla simulator that we used to perform our evaluation. I'll provide a summary of our history accuracy trade-off evaluation before concluding with some future work. Consider the graph shown in the upper right-hand corner of the slide. This graph has 3 nodes, the last of which is a supernode made by combining all nodes from the cycle into one. As a result, if the maximum history age for the cycle is 2 time steps, then a given job of the task corresponding to this node has a precedence constraint on the output of 2 jobs prior. Imagine that other applications in the system have caused the 21st job of the supernode to be greatly delayed. Although it was released at time 100, it cannot begin to execute until around time 114. Note that, despite the delay, the precedence constraint requires that job 21 complete before job 23 can begin. If jobs are executed sequentially, then each job completes before the next can begin. This satisfies the precedence constraint. However, if the cycle utilization is greater than 1, unbounded response times can arise. As shown here, the 24th job has a response time of 7.4 time units, assuming sequential execution. If instead full parallelism is allowed, then jobs 21 through 24 may execute concurrently. Thus, the response time of job 24 is only 2.3 time units. However, as jobs 21 and 23 execute concurrently, the precedence constraint has been violated. Restricted parallelism allows only a given number of jobs of a task to execute concurrently. In this example, that number is 2. Therefore, the precedence constraints are met. The response time of job 24 is 4.1 time units, thus longer than under fully parallel scheduling, but shorter than sequential scheduling. As shown in our prior work, restricted parallelism allows for response time bounds to be computed for cycles with utilization exceeding 1.0. However, allowing the use of older data can impact the accuracy of the algorithm. This impact is what we explored in this paper. To make the source of the accuracy impact more clear, consider execution in which the history age is always 1. This corresponds to sequential scheduling, when the most recent outputs are always available. This is in contrast to execution in which the history age is always 2. In this case, the set of time steps are effectively subdivided into two subsets, one for the odd time steps and one for the even. Data from one subset is never available to the other. This behavior represents a sort of worst case of data availability. Compare this to a system for which the output from the prior frame is usually available, and the maximum history age is 2. In this example, the lightest pink job executes concurrently with the one before it, so it must use older history. It is our expectation that the accuracy should be comparable to that of a system with sequential execution, and much better than when the history age is always 2, but with bounded response times. In this work, we answered 4 research questions. Question 1 addresses the difference between the best case, sequential execution, and the average case. Sometimes older outputs must be used. Question 4 directly looks at the gap between the average case and the worst case. Questions 2 and 3 explore the impact of the maximum history age relative to the frequency of the most recent outputs being available. In this talk, I will focus on questions 1 and 4. For the rest of our results, please see our paper. I will now describe the multi-object tracking application that we use to track vehicles and pedestrians in the Carla simulator. Carla is built on Unreal Engine 4. As a result, it can generate photorealistic renderings of city and highway scenarios, and also incorporate realistic physics to detect and react to obstacle collisions. Additionally, it provides us with the ground truth locations and orientations of all vehicles and pedestrians in the scenes. We've already seen a tracking pipeline for rabbits. I will now give a more in-depth example using an image taken from Carla, rendered from a camera attached to the front of a vehicle. The input to a time step of multi-object tracking is an RGB image, as shown here. We first perform object detection to detect all vehicles in the image. In this case, one vehicle is occluded by the blue car in the center right, so only 2 detections are reported, shown here as solid rectangles. The dots in the image represent the locations from prior time steps for all vehicles tracked in the scene. The next step of the process is to extrapolate the tracks to predict the current positions of all tracked vehicles. The predictions are shown as dashed rectangles. Note that one vehicle has exited the scene to the right, so only 3 are truly still visible. In order to associate current detections with maintained tracks, a matching step is performed on the detections and predictions. Finally, the tracks are updated. For the vehicle that left the scene, the track is deleted. The 2 matched detection-prediction pairs result in straightforward updates to tracks indicated by filled circles. The track corresponding to the occluded vehicle, which was not detected, is updated solely based on the prediction indicated by an empty circle. The output of a time step is the trajectory of each tracked vehicle. This information can be used to make decisions for safe navigation through the scene. I will now describe how we evaluated the impact of available history on the accuracy of multi-object tracking. In our evaluation, we considered 4 scenarios chosen from the Carla challenge. These particular scenarios are ones in which tracking can be particularly helpful to predict the motion of other agents in the scene. In the first scenario, immediately after the ego vehicle, indicated by the yellow star, turns right, a bicyclist crosses the roadway in its path. In the second scenario, the ego vehicle must make a right turn at a red light while navigating traffic coming from the left. In the third scenario, the ego vehicle must cross an intersection on a green light without colliding with the vehicle coming from the right and running a red light. Finally, in the fourth scenario, the ego vehicle must make an unprotected left turn in the presence of oncoming traffic. This video demonstrates multi-object tracking in scenario 3. Each track is shown as a different color, and detections are indicated by green boxes. Note that we first performed our evaluation using ground truth detections provided by Carla. For our evaluation with a deep learning-based vehicle detector, I will refer you to our paper. Recall our 4 research questions, of which 2 will be discussed in this talk. In order to answer these questions, we used probability mass functions to represent distributions of available prior results. In order to evaluate the trade-off in isolation, we perform tracking with all results available, i.e. sequential execution, but sampled from a given PMF to determine which prior results to choose for a given prediction step. For example, using PMF1, the results from 2 time steps prior are used with probability 0.09. In total, we considered 8 PMFs. 4 representing different average cases, 1 corresponding to sequential execution and thus the best case, PMFH1, and 3 representing increasingly worst cases. Vehicles were present in all 4 scenarios, and pedestrians were present in 3 of them. Across 3 metrics, which I'll explain next, there were thus 21 comparisons between the different history distributions. For this talk, I will only present results for vehicle detection in 2 scenarios, as these are representative of our conclusions. Please see our paper for our full evaluation. The first metric we considered is AMOTA. This represents the accuracy in which the identities of the track targets are not important. In particular, the ratio represents the number of errors, unmatched detections, and unmatched tracks relative to the total number of targets in the scene. A perfect accuracy score is 1.0. The next metric is MOTP. This is multi-object tracking precision and is the sum of the ratio of the overlap of rectangles for each detection prediction pair. Again, an optimal value is 1.0, indicating perfect matching. The final metric we considered is the average fragmentation count. A fragmentation occurs when a target becomes temporarily untracked and is later retracked. This can occur, for example, if it is temporarily occluded behind another obstacle in the scene. The best possible value for this metric is 0. Our first research question seeks to compare the best case of sequential scheduling with the average case, in which the most recent data is not always available. Recall that sequential scheduling may preclude bounding response times and thus prevent a system from being certified. Therefore, this question is really exploring the actual price of schedulability. What do we lose by allowing restricted parallelism? For this question, we can compare PMF1 to PMFH1. For PMF1, the most recent results are available with probability 0.9. So approximately 90% of the time, the behavior should be similar to sequential scheduling. And in fact, if we compare the accuracy scores, we see that we lose very little accuracy by sometimes using older results. The accuracy is less than 1% lower than under sequential scheduling. Similarly, precision scores are only slightly lower, and the average fragmentation count is only slightly higher. To compare the average and worst case history distributions, we can compare PMF2 and PMFH2. Using PMFH2, the application must always use results from 2 time steps in the past. For PMF2, however, 2 time steps old results are used only with probability 0.2. As we expect, the accuracy is higher in the average case, the precision is higher, and in fact, this holds for both vehicles and pedestrians in every scenario. We can perform a similar comparison for PMF3 and PMFH4, and in fact, we see the same results. We've compared the best case to the average case and the average case to the worst case. As a final comparison, we consider all 4 average case PMFs, some of which have a maximum history age of 4 time steps, relative to PMFH2, which is a worst case of always using results from 2 time steps in the past, and thus never the most recent data. Across all 21 comparisons, PMF1 and PMF2 always outperformed PMFH2. Furthermore, PMFs 3 and 4 beat PMFH2 in all but 1 comparison each. These results enable us to reach the following conclusion. Allowing the infrequent use of older results in a multi-object tracking application has only minimal impact on the application's history and precision, while allowing the computation of bounded response times for use in real-time certification. In this talk, I introduced the application we considered, the tracking of fast-moving agents in the immediate vicinity of an autonomous vehicle, such as vehicles, pedestrians, or even rabbits. Such tracking can be used to predict the future locations of obstacles and plan a safe path through the scene. I discussed our prior work that introduced the concept of restricted parallelism, which enables response time bounds for applications featuring cycles with utilization greater than 1, and describe the trade-off between history age, response times, and accuracy that this parallelism induces. Finally, I provided an overview of our evaluation using Carla, an urban driving simulator, and our results. In the future, we plan to integrate our tracking application into the control loop in Carla, allowing us to perform broader scale evaluations that measure the trade-off in terms of traffic violations and obstacle collisions rather than just tracking accuracy. In addition, we plan to extend our evaluation to include highway driving scenarios in addition to the city driving scenarios already explored. I have greatly enjoyed the opportunity to present our work, and I look forward to taking your questions.